Welcome to Brain Vision.
Well, let's do part A. In part A, we need to find out the relativistic time interval, which it would take the neutron to disintegrate from the perspective of a stationary observer on Earth. So we need to find out delta t. Delta t is the relativistic time. And in part B, we need to find out the distance which the neutron would traverse before disintegrating. So in part B, we need to find out distance. All right, let's do part A. Well, we are given proper time, delta T naught, and delta T naught is equal to 1000 seconds. So the neutron takes 1000 seconds to disintegrate, which means that proper time is equal to 1000 seconds. Well, the speed of the neutron is also given. The speed of the neutron, v, is equal to 0.999 times the speed of light. This is the speed of the neutron. And now we can find out the relativistic factor, or the Lorentz factor, gamma. Gamma is equal to 1 divided by square root of 1 minus v square divided by c square, 1 minus v square divided by c square. Let's plug in values. We have 1 divided by square root of 1 minus 0.999 square. C square gets cancelled with c square, and hence Lorentz factor is equal to 22.37. 22.37. And we know that the proper time and the relativistic time are related by the following equation. Delta t is equal to gamma times delta t naught. And hence delta t, which is the relativistic time, is equal to gamma. Gamma is 22.37 multiplied by delta t naught, and delta t naught is 1000 seconds. So relativistic time is equal to 370 seconds. 370 seconds. Delta t is equal to 370 seconds. All right. And we can say that the neutron lives longer, almost 22.4 times its original lifetime from the perspective of observer on the Earth. Now let's do part B. In part B, we need to find out distance. Therefore, we use v is equal to d divided by t, and d is equal to v times t. And now d is equal to, we have v equals 0.999 times the speed of light, and the time is 22,370 seconds, and multiplying the two numbers we get 6.70 317 multiplied by 10 to the power 12 meters. 12 meters. Here C is equal to 3 multiplied by 10 to the power 8 meter per second. All right. So the particle cuts a distance of 6.70. So it cuts a distance d is equal to 6.70 multiplied by 10 to the power 12 meter, and the distance between Pluto and the Sun is, let's say it is d prime. So d prime is the distance between the Sun and the Pluto, which is 5.90 multiplied by 10 to the power 12, and thus it is obvious that d is greater than d prime. Here d is greater than d prime. So thus the neutron is expected to reach Pluto. So a neutron is expected to reach the Pluto because d is greater than d prime.